Find the possible rational zeros. This involves the rational root theorem. So I'll begin by labeling the coefficient here is a sub n, the leading coefficient. The number here is a sub 0, your constant term. And p over q, the possible rational zeros, are made up of factors of a sub 0 over factors of a sub n. So what are the factors of negative 33? That's plus or minus 1, plus or minus 3, plus or minus 11, and plus or minus 33. We always include plus or minus to take care of all possible signs. And this is a 1. What are the factors of 1? That's just plus or minus 1. When we write the possible rational zeros, every single numerator needs to be put over every single denominator. In this case, you only have one denominator, so that's pretty easy to figure out what you're going to have here. Here are the possible rational zeros. Now I need to test it out because this is not factorable. So if I need to find all rational zeros, I got to test out these numbers and see what works. I'm going to test it out with synthetic division. The coefficients in my original polynomial become the numbers at the top for synthetic. So 1, negative 23, and negative 33. And now I'm going to start off by testing positive 1. Synthetic division is like dominoes. The first one has to fall in order to start. 1 times 1 is 1. Add these vertically. Negative 1 plus 1 is 0 times this one is 0 plus negative 23 is negative 23 times 1, negative 23. That's not going to give me 0. Let's try testing negative 1. Drop the 1, negative 1. Negative 1 plus negative 1 is negative 2. That's negative 2 times negative 1 is positive 2. You get negative 21 times negative 1 is positive 21. That's not going to give me a 0 either. Let's try 3. 1 times 3 is 3, plus a negative 1 is 2, times 3 is 6, plus a negative 23 is 17. Negative 17 times 3, negative 51. That's definitely not a 0. Hope we find one soon. Let's try negative 3. 1 times negative 3 is negative 3, plus a negative 1 is a negative 4. Negative 4 times negative 3 is positive 12, plus a negative 23 is negative 11. Negative 11 times negative 3 is 33. 33 plus negative 33 is 0. Yeah! You got it. Okay. So negative 3 is one of the rational zeros. But what about the rest? Okay, because we ended with a 0, we got something that factored that went into it evenly. So now we have this new polynomial, or the coefficients of a new polynomial, our answer, our quotient. So we started off with an x to the 3, and we divided by x to the 1, so now we're left with x to the 2. So this would be 1x squared minus 4x minus 11. And of course, that is equal to 0 because this entire thing, if you want to find any zeros, you have to make the whole thing equal 0. You have to turn the output f of x or y into 0. If this is factorable, then we find more rational zeros. If it's not factorable, then there are no more rational zeros. This is a 1, so let's try p's and q's. Are there two numbers that multiply to give me negative 11 and those same two numbers add to give me negative 4? No, the only things that multiply to give me 11 are 11 and 1. That's not going to give me negative 4. So this quadratic right here will 100% give you two more answers. But those answers will not be rational because this right here is not factorable. So we had our possible rational zeros, and then the only rational zero that ended up popping up was negative 3 right here for this polynomial. Number 14, find the possible number of positive and negative real zeros. So we're going to use Descartes' rule of signs. Okay, so Descartes' rule of signs counts the number of sign changes and helps us understand how many positive or negative real zeros. The sign changes in f of x, what you're given is going to be the possible number of positive real zeros. Positive real zeros are affected by the sign changes of just f of x. So let's see, what do we have here? A positive 15 to a positive 5. That's not a change. A positive to a negative. That is one change. A negative to a negative, that is 0 change in sign. Negative to a positive, that's another change. Positive to a positive, that is no change in sign. So how many changes? 1, 2. 2 possible positive real zeros. Also, 2 minus any even integer until you reach 0 or negatives. So what is 2 minus the smallest even integer, which is 2? So what's 2 minus 2? That is 0. So there could be 2 positive real zeros or 0 positive real zeros. Now to find the negative real zeros, we need to test what's happening when we plug in negative x to all the x inputs. When you plug in a negative x, it changes the signs of only some of the numbers. But which numbers does it change the sign for? So negative x to the power of 5 is negative x times negative x times negative x times negative x times negative x. Anytime you have two negatives, that equals a positive. So negative times negative is a positive, times another positive, times a negative. So when you had negative x to the power of 5, it changed the sign, and you ended up with negative 15 x to the power of 5. But let's look at negative x to the 4. Negative x times negative x times negative x times negative x. Anytime you have pairs, like I said before, that's a positive. Negative times a negative is a positive. If you have an even exponent, negative x to that even exponent, it does not change the sign. It's going to still be x to the 4th. Okay, so this is an odd exponent, so the sign will change. It'll be plus 108x cubed. Negative x squared is just a positive x squared. So this will remain negative 36x squared. Plus 108 times negative x, that definitely changes the sign. It's negative 108x plus 36. Now take a look at the sign changes. Negative to a positive, that's 1. Positive to a positive, that's not a sign change. Positive to a negative, that's another change. Negative to a negative, no change. Negative to a positive, that's one change. Okay, so 1, 2, 3. There will be 3 possible negative zeros or 3 minus an even integer until you reach 0 or a negative. So what is 3 minus 2? That's 1, and 1 is also a possibility for the number of negative real zeros. Number 16 is asking us to, again, state the possible number of positive and negative real zeros for each function, but then to also factor and find all the zeros. So starting off, we're going to go through Descartes' rule of signs of f of x to get the positive real zeros. There is positive to negative is one sign change. One sign change, another one, another one, another one. Wow, that is a total of 5 sign changes. So positive real zeros could be 5 or 5 minus the even integer 2. So it could be 3 or 3 minus the even integer 2. 5, 3, or 1 is the possibilities for our positive real zeros. Now we're going to evaluate f of negative x. Remember, inserting negative x only changes the signs of exponents that are odd. So negative x to the power of 5, that does change the sign, and that would be negative 3, x to the power of 5. Minus 6 times x to the power of 4 to the even doesn't change. This would be minus 22 because this one's to the power of 3. This one stays minus because it's negative x to the power of 2. This one becomes minus 35x minus 70. If you notice here, every single one of these signs is negative. So there are literally 0 sign changes happening here. So 0 negative real zeros. Okay, so we've completed the first part, but then they said factor each and find all zeros. So we need to try to attempt to factor this. Now, we could use synthetic division and the rational roots theorem to start breaking this down and finding easier things, but I think I might be able to factor this. I call this one mega grouping, because this time you'll have 3 little groups. You'll say, okay, let's factor just these 2 terms, and then just these 2 terms, and then just these 2 terms. So we're going to make the equation equal to 0, so we can factor and solve for the zeros. What is common between 3x to the 5th and 6x to the 4th? 3x to the 4th. So 3x to the 4th times what gives me 3x to the 5th? You're just missing an x there. And what do you get when you take this term and you divide this term? You get the negative 6 divided by 3 is negative 2, and x to the 4th is already there. Plus, what can we take out of this? Oh, x to the power of 2, and 22 goes into 44. So I'm going to take out a 22x squared. That leaves me with x, and then 22x squared times what gives me negative 44x squared? That would be negative 2. Factor out of this one. 35 actually goes into 70, so positive 35 times x minus 2. If you notice, you have 3 products here. You have 3x to the 4th times x minus 2, 22x squared times x minus 2, and 35 times x minus 2. So all 3 of these products actually have a common factor, which is the quantity x minus 2. So when we divide each of these terms by x minus 2, we're taking it out, right? This is left with 3x to the 4th plus 22x squared plus 35. Let's continue to factor. Here, this one has an x to the power of 4 and an x to the power of 2, and then no x's here. That is called quadratic form, when this one is half of this one, and there's not an x here. So for quadratic form, we can actually use any of our regular methods like double cross or slip and slide or grouping, however you want to do it. So the 2 factors of 3x to the 4th, you really just have 3x squared and 1x squared. And then you need 2 factors of 35, and those products will end up hopefully giving us the middle term, 22x squared. So what goes into 35? I was thinking immediately 7 and 5. If I do 7 times 3, that's going to be 21. And then a 5 times 1, that's not going to give me 22. So then I tried 7 and 5, 3, and then we multiply across the diagonals, right? So 3x squared times 5 is 15x squared. And x squared times 7 is 7x squared, and that does actually add up to be a positive 22x squared when both of these are positive. We have factored it further. Okay, top row times bottom row, 3x squared plus 7 times x squared plus 5. Now these little squares, they cannot be factored further. There's not a GCF, and it's not a difference of perfect squares. So you have completely factored this, and now our job is to use the zero product property to actually solve for those zeros. Here is our first one, x equals 2. That's one answer. How many answers do I need a total of? 5. Continuing on, make this equal to 0. 3x squared plus 7 equals 0. Minus 7 on both sides. 3x squared equals negative 7 divided by 3. X squared equals negative 7 over 3. Now we're going to square root both sides. X is equal to plus or minus the square root of negative 7 over 3. I'm going to separate the root to be square root of the numerator over square root of the denominator. I have to do this in order to rationalize, but before rationalizing, take out the I. This negative under the square root means that there should be an imaginary number. So put an I in front of square root 7. That's over square root 3, and rationalize by multiplying by square root 3 over square root 3. That gives us our final simplified version. So I is still in front. Root 7 times root 3 is root 21. And root 3 times root 3 is 3. Positive or negative. So that's 2 more answers. X squared plus 5 equals 0. Subtract 5 on both sides. X squared equals negative 5. Now we're going to square root both sides. X is equal to plus or minus the square root of negative 5. But when you have a negative under the square root, that is the imaginary number outside of the square root. So x is equal to, and if you want to see it, it would be negative 1 times root 5. So you can write that as a product. And then the square root of negative 1 is I, and we write it as square root 5. Do not leave negatives under square roots for your answers. Ever.